others have noted that there's been a lot of issues in the literature with interpretation of XPS spectra, and in particular, the interpretation of the metals, the transition metals XPS. There's been kind of a proliferation of faulty data ongoing within the community, where there's some citing of erroneous data, and this is even happening in high impact and well-regarded journals. So the point kind of is that XPS is not just a point and shoot type technique. There is a need for expertise on both the analysis side and on the interpretation side of things. And so I and many others in the XPS community, and these are just some of the publications that we've put forward in that regard, have been working to kind of fix this. And I know this is not just an XPS issue. There's been struggles in the broader analytical community with these sorts of problems. Some of the work here, we started back in I started back in about 2004, looking at things like chromium and iron. We're trying to figure out, how to better interpret these spectra. And over the years, we've published quite a number of papers that have been quite well received and highly cited over the years. We started this work, this instrument in the foreground is the Kratos Axis Ultra, which is what we kind of started this work on. This instrument was purchased back in 2000. It was recently replaced in 2018 at the front. Here's the Kratos Axis Supra. This is a high research grade type instrument with all the bells and whistles. It's got an aluminum K-alpha source, a silver source. You can heat the stage up to 800 degrees, cool it down to liquid nitrogen temperatures. You can fracture samples in situ in the vacuum. There's a glove box that hooks up to the front end of the instrument somewhere right about here that you can introduce air sensitive and water sensitive samples. It also has a gas cluster ion source, which allows you to do depth profiling through soft materials. The instrument in the background is the Kratos Axis Nova. That's more of a high throughput type instrument where you have a large sample platter and you can put a whole bunch of samples on and set it up for automated runs. XPS in brief, you start with X-rays, so aluminum K-alpha X-rays at 1486.7 eV. You knock out a photoelectron, you measure the kinetic energy of that photoelectron, and using the Einstein equation, you can calculate the binding energy of those electrons within the core of the atom. XPS is a very surface sensitive technique. You're looking at the outer 3 to 10 nanometers of the surface. And using it, you can identify and quantify the elements present. So we have over here what we call a survey scan, where you use all these peaks, and the areas under these peaks in relation with relative sensitivity factors can give you how much of the different elements you have present within the material. If you zoom in on a peak, say the carbon 1s peak, that's this over here, what you call a high resolution scan, you can get the chemical state of those species. And so we have carbon bound to carbon here, and up here we have carbon triply bound to fluorine and all sorts of species in between that you can calculate how much of those that you have. So the various chemical states. XPS chemical state determination theory. So small shifts in the core level binding energies are indicative of chemical state changes. So you can tell whether you have metal versus oxide, silica versus silicone, etc. As you withdraw valence electron charge, you decrease shielding, increase the binding energy. As you add valence electron charge, you increase the shielding, decrease the binding energy. So that's the theory. In practice, there are lots of databases that allow you to find a binding energy, and for many uncomplicated peak shapes, a binding energy reference is sufficient, and that's all you need. So things like the NIST database or the Phi handbook. Literature values can be very good. Some places it's incomplete. They just standards haven't been taken for a lot of materials. And then there's some wrong answers out there as well. So, how do you believe the literature? You have to do your homework. Some of the things you can do, you can check the literature for the calibration of the instrument. That's a big issue. What they're using is charge referencing. So non-conductive samples will build up an electron charge on their surface that has to be compensated for. You have to take those things into account. So are you referencing to an external standard such as gold? internal standards such as the adventitious carbon or a known component of the compound, etc. When you get into the transition metals, things start getting a whole bunch more complex. You have contributions from spin orbit splitting. You can have asymmetric peak shapes, loss structure, shakeup structure, and then the big one is multiplet splitting. And for all of these materials, you can get overlapping binding energies and varying peak shapes for many different species. So what do I mean by that? So if you look up here, this is a titanium metal. This is the titanium 2p spectra. And you can see that we have an asymmetric peak shape for that metal, whereas something like the oxide would have a simple Gaussian-Lorentzian type peak shape. Copper hydroxide, copper 2 species is the classic example for showing shakeup structures. So these peaks here above the main peak are what we call shakeup structure, and they're indicative of a copper 2 species, whereas copper 1 and copper metal do not show these. Over here we have chromium 3 oxide, and we have this complex peak shape for chromium 3 oxide. And one of the things we saw in the literature was that people would take a look at this and say, okay, instead of saying, well, this is the multiplet structure of chromium 3, they would try to assign and say, okay, this is chromium 2, chromium 3, chromium 4, chromium 5, chromium 6. And some of these species don't even, they're not realistic, don't realistically exist, or they're very rare. So we're seeing those kind of errors in the literature. The species in red here are those that will show multiplet splitting in their structure, the peak shape structure. The ones in green have no unpaired electrons, so they don't show any multiplet splitting. And the ones in yellow have multiplet splitting, but it's either not well resolved or it shows up as peak broadening only. So with all these complications, how do we identify the species that are present, and how do we quantify the species that are present? And so that's what a lot of this work has been done to do. And our solution has been to first do a survey of literature databases and a compilation of literature references to see what's out there, and then do an extensive analysis of quality standard samples. And so then we take the fitting of those spectra from those standard samples and take into account all the previously mentioned phenomena, including spin orbit splitting, peak asymmetries, loss structure, shakeup structure, multiplet splitting, and then use the total photoelectron yield for each species. So all the structure, all the shakeup structure that's attributed to each species to determine the present of the percentages of those species present in unknown samples. So if you look at species without significant multiplet splitting, we have look at some of the reference spectra. So we have an asymmetric peak shape for the metal. For the oxide, we have these doublets here, of course, with spin orbit doublets that have constrained values of being areas of 2 to 1 and specific spacing between those species. And then we can put that all together into a peak fitting routine that takes into account all these things. And then we look, just the area under the curve tells us the area of the amount of the different species present. For species with significant multiplet splitting, as I mentioned, we started with chromium, where the literature was generally not very good. We even had databases that were quoting single peak binding energies for compounds that were known to have multiplet split peaks. So, where do you pick that peak? And again, the multiplet peak structure was improperly assigned to various chemical shifts. Some of the issue may have been resolution of older XPS instruments, but mostly it was just that the people didn't understand that these phenomena were occurring within these spectra. And so how do we go about doing this? We take a series of standard samples, do analysis, quality analysis. We devise peak fitting routines for each peak. And so that's what this looks like, where you have, for say, chromium 6, you have a single peak because it has no multiplet splitting. You set what its full width half max is. You set its binding energy range. For the chromium 3 species, for something like chromium 3 hydroxide, you can fit it with one broad peak set to a specific binding energy and a specific full width half max. For the chromium 3 oxide, you have these 5 multiplet peaks with set spacings, set areas, basically mimicking the shape of the standard sample. And then with the metal, you have an asymmetric peak shape that, again, you mimic the shape of that peak for the curve fitting. And you put that all together and you can pull out, okay, I have so much chromium-3 oxide, so much chromium-3 hydroxide, so much chromium-6 within a material. For nickel, same sort of thing, where we have nickel metal has an asymmetric peak shape with some satellite structure. The nickel oxide and nickel 2 hydroxide have very different peak shapes. They have lots of different structure in there, so it's diagnostic of what you have. And I should note that out in the literature, even now, we're still seeing cases where people are taking this, instead of saying, okay, this is the whole peak shape for nickel oxide, they're saying things like that this would be the nickel 2 and this is nickel 3, where really all they have is nickel 2 oxide. And again, if we look at things like the ferrate and the chromate, and then an actual nickel 3 compound, we have different structure as well for each of those. So what you end up getting is these large tables that define these peak fitting parameters. And the reason why we do it this way is so that we can take these fitting parameters and apply it to a whole bunch of different software packages that are used out there by different XPS practitioners. And if we were to just use to give overall peak envelopes, it wouldn't work, because different instruments have different resolutions. It doesn't allow you to slightly shift the spectra around if you have some changes in calibration or changes in what you use as your binding energy calibration. And so doing it this way allows use by everyone. And what that looks like, you can see that, and these parameters work for a large number of samples. We've been using them for 10 or so years now, at least. We've had very good success with them, being able to pull out chemistries from different materials. And I should mention that really what we're doing, even though it looks like a whole mess of peaks here, you can see all these different peaks that are there, all we're doing is mimicking the overall peak shape of the standard samples. And this is not a new phenomenon. People do this in infrared spectroscopy and other spectroscopies, where they're taking standard spectra and using them to pull out what they have in a mixture of materials. So we've done similar work for manganese, cobalt, iron. With manganese, you have a mix of manganese 2, 3, 4, 6, 7 oxides, oxyhydroxides and hydroxides, so a bunch of complications there. Cobalt is the same. There's a whole bunch of different species for cobalt. Iron is probably the worst one to get information out of. There's iron 2 and 3 species. You have things like FeO, Fe3O4, Fe2O3, both the alpha and gamma phase, FeOH, alpha, gamma, and there's some beta phases as well. A large variety of species that all have unique multiplet structure and shakeup satellites. They all overlap. The satellite structures from the Fe2p 3/2 peak overlap with the Fe2p 1/2 metallic peak. And so as your oxide hydroxide mixture grows in complexity, our ability to quantify or even identify species for iron decreases. If you have 2 species plus the metal, these work very well. For 3 species, moderate to good success, depending on the species present. And then 4 or more species, it's unlikely that you can reliably say there's anything beyond you have iron 2 and iron 3 species. So if you can get complementary analysis by, say, Raman or grazing angle XRD, that's very useful. And here's some examples of different iron species. And if you look at the peaks, right, it just looks like, you know, this all kind of looks the same, but there's enough change in the structure in here and enough change in the binding energy shifts that we can pull out the different amounts of things that are present here. So for here we have Fe3O4, Fe2O3, but over here we have FeO and Fe2O3. And if you're looking at a series of samples such as these, you can really see changes, and you can prove to yourself, yeah, this is working. We are seeing these changes within the peak structures, and being able to quantify to a degree as to how what we have in these species. And so if you take that kind of curve fitting and combine it with other information that you have about the sample, so in this case, we take the curve fitting of nickel, chromium, and molybdenum to get at the chemical species that are present, combine that with the data that we're getting from the survey scans, we can then kind of get with simple math, we can then pull out, well, what's going on at these surfaces? And you can kind of say, okay, here we have this much metal, these are different metals, and these are all the different oxides present. And as we go to this next sample, we have much less metal. So first of all, we know that, okay, this is a thinner oxide system than this because we're seeing less metal. And if you combine this with things like Auger and XPS depth profiling, angle resolved work, then you can then push this even further to say, okay, I have these species present, but now I can tell, okay, what's the layering of these species? What's at the surface? What's in the middle of the oxide? And then down into the metals that are present. So the idea is to pull out as much information as you can get from these spectra. So not leave anything on the table, so to say. Our group is doing a lot of work with a company called the NWMO, which is the Nuclear Waste Containment Management Organization. The job is to bury our spent nuclear fuel underground for the next 10,000 to 1 million years. And what we call this is the deep geological repository. And what they're going to do, they're going to take these large metal, iron or steel containers, coat them with pure copper, a 3 to 5 millimeter thick layer of copper, and bury these underground for a long time. So we've been doing a lot of work with copper, trying to understand the corrosion of copper. And you can see if this is kind of a survey of different copper species. You can see that in the copper 2p spectra, we have all sorts of different shapes and positioning of the copper 2p and shakeup structure, for these are our copper 2 species. If we look at the Auger peaks, the LMM Auger peaks, we can also see that we have different binding energies or kinetic energies and shapes for the different species that are present. So we're going to use that kind of information. And so with copper, we do a whole bunch of different things where we look at the binding energies of the main peak. We look at what's called the modified Auger parameter, which is an addition of the copper 2p peak and the kinetic energy of the Auger peak. And that can tell us information about what's present. We can do curve fitting of the 2p spectra. We can take a look at how much of a shakeup structure we have versus the main peak structure and do some math there where we figure out, okay, I have so much copper 2 versus copper 1 or copper 0 species. And then we can do curve fitting of the Auger spectra and again derive what materials we have. And this is particularly useful for copper 1 species. If we go back here, copper 1 species and copper metal have basically this one sharp peak that overlaps, and it's almost, there's very little shift for any copper 3 or copper 1 species, but there's a lot of change in the structure of copper 1 species in the Auger structure or Auger peak. And so we can figure out how much, you know, for example, how much copper 1 sulfide versus copper 1 oxide we have. And so that's the kind of our latest work that we've been doing. This is a website I run called X-ray Photoelectron Spectroscopy Reference Pages, or xpsfitting.com. And it's a repository of binding energies, curve fitting techniques, explanation about how XPS works, some tips and software usage tips. So this is something I started about 12 years ago. It gets viewed somewhere around 20,000 times a month by users around the world looking at XPS.